Okay, that was some terrible underlining, but we're going to look at this today. We've done quite a bit already. So we've done shear flow in different sorts of cross sections, both closed and open. At the moment, all of the sections we've dealt with have been straight. They've been at some sort of angle, perhaps. I haven't gone through with you how we can look at varying thickness sections, but I gave you guys an example where we had a section that looked sort of like this. Okay, a section that looks like this. If we want to find out where the shear center of this is, it's obviously going to be somewhere along this line of symmetry. The only thing that's different with these sorts of sections is that if I defined an ordinate S1 here, and then I wanted to work out the shear flow distribution, QS1 is equal to minus Vy on Ixx, where Vy is this arbitrarily applied force. Vy on Ixx integral from S1 to 0. The thickness is then a function of S1, okay? And then y is actually a constant, but I'll put it as a function of S1 in here, ds1. So all you have to do is work out the function that produces this, and we can probably see from something like this, this was T1, this is T2, and if this base was B, then thickness as a function of S1 is going to be equal to T1 plus T2 minus T1 on D multiplied by S1. Okay, so we've got a linear function of S1 to put in here. I'm not going to go through that example with you because I've assigned it as an example in the notes, and if you are having trouble, come and find me about that. So we're not going to look at that today. What we're going to look at is the next more complicated part, which is looking at shear flows in curved parts of sections, specifically looking at semicircular sections, because we can define nice equations that describe those sections for us. So if I were to give you a wing section, for example, that was a closed section that looked like this great image that always ends up looking a little bit phallic. If I had a section like this, then we could work out the shear flows, say S1, S2, S3, S4, and S5. So at the moment we know how to get this one, this one, this one, and this one, but what we don't know how to do is this semicircular section here. So I'm not going to go through an example that looks just like this. I'm going to go through an example from Megson where he goes through these semicircular sections. This great one here, if this example I did always ends up looking a bit phallic, it's very hard to draw this without it looking like a sort of child's drawing of a comical set of breasts, so I apologize for that. If I start giggling, it's because I'm juvenile. Okay, but we've got this section here, or this object. Can I move this around? Here we go. So this is the example from Megson. Let me just clear up this a little bit. Let me clear up my title so I can write all over this. In fact, I'm going to make a new sheet and I'm going to copy this in again, because for some reason it's an angle and I don't like that. So we're going to look at this shape here. Okay, so it's section. The question is asking to determine the position of the shear center S for the thin-walled open section shown in this section, and the thickness is constant, and he gives us the answer. So that's what we're trying to find. I like these sorts of questions because if we don't find this answer, we haven't solved the problem. So we've got these two sections, and what we're looking for, let's just do a little bit of drawing on here. The actual section itself is very clearly these two semicircular sections here. Okay, so what's drawn here is just a line denoting where they start and end and showing that they are semicircles, and what's given here is the radius and then the thickness of these sections. So we can see that this is symmetric around a line of symmetry that exists here. So in order to determine the shear center of this object, we are going to have to apply some vertical force here, and then I'm going to try and determine what my shear center is. And I'm going to give this the symbol, let's call it, let's give it a letter that I'm unlikely to use in this. Let's call this E. Okay, E in this question. And that brings me to another point here. When we were first looking at the reason for why we're looking at all of this stuff, I mentioned the concept of an elastic axis. So we've got a wing section like this, and we've got a flexural center, which is the which is the shear center of this wing. And we've got then, for example, we've got the aerodynamic center where we've got lift and the pitching moments. The distance between the flexural center or the shear center and the aerodynamic center is given the symbol EC. Okay, that's the elastic axis, where E is a non-dimensional distance denoting the distance between here and here. Okay, so the E that I've just used here isn't the same thing. But that's the beauty of mathematics and algebra. The letters are just placeholders meaning what they mean at that point in time, okay? And I could pick another letter. So I sometimes use zeta, but zeta's really hard to draw. But you guys need to get out of the habit of thinking, oh, I've seen that letter before, so it must equal this. Students make that mistake a lot. If they see a T, you know, sometimes T is thickness. You know, some students would invoke, oh, well, time is equal to, we know that speed is equal to distance divided by time. So t must be equal to velocity multiplied by distance in this sense. Okay, so yeah. Okay, do I obviously haven't arranged that question properly at all there. I've done that incorrectly there. Apologies. I'm trying to come up with this as I go along. Would I say that time is equal to distance divided by velocity? You couldn't substitute those two in because t here, this is coming from kinematics, which is velocity is equal to distance divided by time. This is time equals t here. Just because you see a letter in an equation, in a formula, you really need to think about the context in which it's been given. So I've chosen E here to denote this arbitrary distance that I'm going to determine between Vy and this point here. Okay, I've just called it E. It's not the same thing as the elastic axis in the previous examples. It's just a letter. That's mathematics. That is also aeronautical engineering. We reuse letters all the time. Lift is L. Rolling moment is also L. Okay, thickness is T. Time is often T. S is often displacement. S can also then be lots of other things depending what we're looking at, okay? So just when you see an example like this and you see a letter, think, what does it mean in the context of this problem, okay? So this one here, E is just this distance between this arbitrary force and this bit up here. So in order to look at this problem, I'm going to call this 1, 2, and 3, and I'm going to define two shear flows. So I've got S1 going this way, and S2 going this way. From the symmetry of the problem, I can see that S2 is got to be equal to minus S1, which is great for us because we don't really need to solve both of them. We can just solve one of them and double it. So what we're going to try and do is evaluate moments, say here, and we can then look at the moment caused by this shear flow, double it, and that's got to be equal to this Vy multiplied by that E, okay? And this S1, the moment caused by S1, is going to be a function of Vy. That'll cancel, and we're going to get a value for E that we certainly hope is going to be equal to pi r divided by 3. So we're going to get there. There's a lot of complicated things to do in order to get there, and this problem that I'm about to solve is probably more than I would expect most of the class to be able to do. But now I can point out the bits that we're doing along the way. You will be able to use elements of this. I've deleted that bit annoyingly. You will be able to use elements of the solution to help solve a wing problem or a wing torsion box with a curved section. So we're going to go through that. So our generalized expression that's going to help us in here, we know that QS1 is equal to minus Vy on Ixx multiplied by the integral S1 to 0, thickness multiplied by y bar, which is the vertical separation from the centroid, as a function of S1 multiplied by, integrated with respect to ds1. So that's what we're going to need to solve. There's two things that we don't know how to do yet, or you don't know how to do, but we're going to work out how to do them. So we don't yet know how to determine the first one, Ixx of these semicircular sections. And the second one is, once we've got these semicircular sections, how do we determine the part of the shear flow, the bit of force, what direction it's in, and how that causes a moment here? So we need to think about that. So we need to think about how to define MQ for a semicircular section. So we need to look at these two things, and I say we don't yet know how to do these. I think actually the theory that we're going to go through here is just a bit of elementary mathematics. So we're going to go through that, understand it, and you'll think, oh man, I could have worked that out on my own. Okay? But that's the beauty of some of these things. If you try and look at these problems, you maybe just need, you can get 95% of the way there yourself, and you just need a little bit explained to you, and that's great. So we're going to look at these two separate things, and that's going to help us determine them. I can't fathom what my upstairs neighbours are doing, but my goodness, it sounds like he's wearing clogs. So we're going to look at these two things separately. So I'm going to look firstly at how we determine the second moment of area of a semicircular section. So let's draw a semicircle here. So this is my semicircle. We know that since it is symmetric, it has a line of symmetry along here. That along here, the centroid must lie somewhere. We don't know where it exists along here. So if, for example, we wanted to determine the IYY, we would need to know the horizontal location of the centroid, because we'd need to look for X bar. Let's just put these two lines on here, Y and X. But because we're just looking to get Ixx, we know the equation that gives us Ixx, by definition, Ixx is equal to the integral of the thickness multiplied by y bar as a function of s, all squared ds. And that's where we've got this ordinate s that extends around here. So because we only need to know the vertical separation, we only need to know the vertical location of the centroid, and that's fine. So then our displacement is just going to be a function along here. And then now we've just got a little bit of algebra to work, or algebra and geometry to work out on here. So let's say this is a semicircle, imagining I'd drawn this properly. I've got this distance, which is constant, r. I've got an angular displacement, which I'm going to call theta. So two things I can work out from here. This y bar as a function of theta, y bar as a function of theta is simply equal to r cosine theta. Okay, so that's the separation from this point here. R cosine theta is that length here. Then also I've got this arc length along here, which is going to be my s. So s as a function of theta is simply equal to r theta as long as theta is in radians. So s is equal to r theta. So I can get t, which is constant. I've got my y as a function of s squared. This is ds, and I've got r as a function of theta, so I need to do an integration change of variable. Again, bit of elementary calculus. We've got s is equal to r theta, ds is equal to r d theta. Okay, so we can just replace the ds with an r d theta, change the limit from 0 to pi here, and that's going to give me the integral here. So let's say Ixx is equal to, we'll take the thickness out, we'll make it an integral from 0 to pi, and then I've got my r cosine theta. Let's just square that. R squared cosine squared theta multiplied by, well, not multiplied by, sorry, the variable of integration was s, and I'm going to change that to r d theta. Okay, so I've got this now. Let's just get rid of this overzealous centroid line. Ixx is equal to, I can take the r out of here, so we've got t multiplied by r cubed, and then I can integrate this, so cosine squared theta integrated gives me half theta plus sine theta cosine theta. Okay, I sometimes forget these integrals for these, so because all of this course is open book, you can just plug this into Wolfram Alpha. Okay, I remember techniques like integration by substitution, but the actual sort of definitions of the integral of cosine squared theta, I sometimes forget those things. Okay, but because this course is open book like life, you can just look some of these things up. Okay, thankfully we get integral of cosine squared theta gives me half theta plus sine theta cosine theta. Because our limits are pi and 0, this will always be 0, which is nice. So my Ixx for a semicircular section is equal to t r cubed multiplied by pi divided by 2. Okay, so this is always going to be the second moment of area, Ixx, around of a semicircular section defined about its own centroid. Okay, so it's always going to be defined about that vertical line of symmetry for our shape. So we can use that now to help us determine the full Ixx of this entire shape. So we don't just have one of these, we've got two. So we've got one semicircle, second semicircle, looks a bit like a bum. So we've got these two here. Now the centroid of each of these is going to be sort of through here, and the centroid of the entire shape is this line here. Okay, so we can just work out the contribution from one of these and double it, and that will give us the total Ixx using the parallel axis theorem. Ixx is equal to 2 multiplied by whatever Ixx prime, which is the Ixx around its own centroid, plus a multiplied by y bar squared. Okay, so the bit that we just worked out is, it's a shame that line didn't go in there nicely, is this part here. We now can work out these two other components. So if I've got a semicircle that has radius r and thickness t, we can work out the area now. Okay, so the area of an annulus, if I've got a circle, area of an annulus is equal to pi multiplied by r outer squared minus r inner squared. So for our purposes, the area of a semicircular annulus, so semicircular annulus is equal to the half pi r out squared minus ri squared. Okay, so our r out for this is equal to r plus t on 2 plus half the thickness. And then our r inner is equal to r minus t on 2. And because we're dealing with small thicknesses, you can, when I first went through this, when I did a derivation before last class, I had the inner thickness as being r and the outer thickness as being r plus t. Because these t's are eventually going to cancel, it doesn't actually matter, and that's because we're treating t's as being small. But we'll go through it this way, but I'll leave it as an exercise to you guys to try it the other way if you wish. So our semicircular annulus, the area is half pi r plus t on 2 squared minus r minus t on 2 squared. So we'll expand both of these. Half pi r squared plus 2t, so I'm going to, this one's r squared plus this multiplied by this doubled. So it's going to be plus 2RT on 2, so plus RT plus T squared on 4 minus R squared. And then I've got a minus, and I'm going to get 2 minuses here, so it's going to become plus. So I'm going to get plus RT, and then I'm going to have a minus, and these become a plus, it'll be a minus. No, it is a minus here. Minus T squared on 4 here. Yep, okay, that's good. So actually these two cancel anyway, the way I've done this. So these cancel here, but also because t is small, t squared is irrelevant. We can ignore it, okay? Yep, that's fine. So what we end up with here, and also these r's obviously cancel, so that's r squared cancel. I've got half pi multiplied by RT. So I end up with, multiplied by RT plus RT, so we've got 2RT in here. This is going to become pi RT. I'm trying to think a couple of steps ahead, and I then can't narrate the step I'm currently on. It's actually pretty hard to do maths and talk about it at the same time, I've discovered. Okay, so this here is the area of my shape. That's the area of a semicircular annulus. And then the y bar, now got the area of the semicircle, and we can now populate everything in here. We just need to know this y bar. Y bar is just the distance between the two centroids of those whole shapes, basically. So if I've got my whole shape here, the centroid of this lower shape is just its own line of symmetry. So that will be r. So then my r is my y bar, which needs to be squared to go in here. So the total Ixx of this shape is equal to 2 multiplied by the Ixx of the semicircle about itself. So that is t r cubed pi on 2. Plus the area, which is pi RT, multiplied by y bar squared, which is r squared. So let's sort this out. In fact, let's multiply this through. So this is t r cubed pi plus 2 pi r cubed t, which is 3 tr cubed pi. Okay, so that is the whole second moment of area Ixx for this entire shape. So this is the one that we use inside our shear flow equations. Right, okay, so we've got that far now. Let's get back. So we said on here, things that we don't know how to do were Ixx for semicircular sections. We know how to do that now. So if we know how to do not just Ixx of semicircular sections, but we know how to do Ixx semicircular sections, put two of them together, and we've now got that Ixx, which is this bad boy down here. Okay, you probably won't need to do this bit again, but you'll certainly need to be able to determine the Ixx of a semicircular section, which we did here. So you'll certainly need to be able to use that in the future. So now we're going to define MQ for a semicircular section. So we're actually not going to get to this bit yet. We're going to first need to work out what the shear flow distribution is in this shape. So let's have a look at that. Because we remember that actually I only need to do it once, and I can just double it for this shape. So let's determine the shear flow distribution in the lower half. Okay, so I'm determining QS1. QS1 is equal to minus Vy on Ixx, and then I need to do the integral. S1 to 0, thickness y as a function of s1 ds1. So there's some different things that we don't know yet. Let's just draw our shape out. So that's my semicircle. My S1 is the ordinate extending around the edge this way, okay? We're going to want to do another change of variable because we'd like to integrate in terms of theta rather than in terms of s, so we'll just do that again on here. I'm going to take the thickness out of here as well because it's a constant, so I've got minus Vy on Ixx integral from theta to 0 y bar as a function of theta multiplied by r d theta. We've already done this substitution before. ds is just r d theta for these shapes. So we need to know what this y is. So this y displacement now is going to be whatever the distance is from the centroid of the entire shape down to where we are on here. So it's going to be y as a function of theta is going to be minus r, which gets us to the center, minus r cosine theta. Okay, just basic geometry, guys. Okay, think about if if I'm down here, then the distance I'm at is at minus 2r. When theta is equal to 0, that's equal to 1, that gives me minus 2r. Okay, when theta is equal to pi, cosine theta is equal to minus 1, that gives me minus r plus r equals 0. Okay, so we just always sense check those distributions we produce. So we can now substitute this into here. I left a t out of that one up there. Let's put a t in. And in fact, let's take this, because these are both minus, this is a minus. Let's just turn that into a plus and say we've got r plus r cosine theta r d theta. Okay, so let's take these r's out as well. Actually, we're going to have a function of r squared here, and I should have really put that in a bracket there. So let's get rid of this if I can. So I can see I'm going to have an r squared here, so let's just get rid of that. Equals Vy on Ixx dot tr squared. And then it's going to be the integral theta to 0 of 1 plus cosine theta. D theta. Okay, so then I can do this integral nice and easy. I get Vy on Ixx tr squared, and then that's going to become a theta, and I'm then going to get plus sine theta from theta to 0. In fact, because I've got the limit of theta and 0 here, and sine theta goes to 0, I can just get rid of these limits, and that will then be the integral evaluated for those limits there. Okay, so I've got that here. I know my Ixx. That should not have been the eraser. Let's try and put that back. There we go. So we know what Ixx is. We've got it from previously. Let's dig it out where I found it. Let's just copy this. So this goes up here. Let's make it a little bit smaller so it's not a giant IXX. Okay, so I can now put this in here. Okay. Right, so some things are going to cancel, which is nice. The T's are going to cancel. And I'm going to just have us get rid of 3 on here, get rid of that. Yeah, that's good. All of these things sort of cancel. Vy on 3r pi theta plus sine theta. So what I've got here is QS1 as a function of theta. Okay, and we can leave it as a function of theta because we're just going to integrate as a function of theta instead. So we've got this, and this is also then therefore equal to minus QS2 as a function of theta on there. We'll leave that. Okay, so we've got our shear flow distribution for that lower semicircle. We know that the integral of that, or the force associated with this that produces a moment at 2, has to be the same as the moment produced by Vy multiplied by E. So we need to think about how we actually determine that force now. Now, there's a lot of nasty geometry in this next bit of the problem, but once you've been shown the equations you need to use, you should be fine. Okay, so this next bit is a bit of a nasty bit of geometry. This is a really horrible problem in the Megson book, but once you know the theory of how to do it, you don't need to derive this stuff yourself, which is pretty useful. So let's have a think about what shear flows mean and the forces that are involved in them. So if I've got a member, let's draw this a little differently actually. Let's say I've got 3 members here. Sorry, that's 2 members. And I've got S1 and S2 along this way. So I'd have an associated QS1 and associated QS2. This angle here, let's just call this alpha. So if I want to evaluate the moment at S1, then sensible choice, because evaluate moments at this point here, let's say this is node 1, 2, 3. If I want to evaluate moments here, the shear flow, QS1, produces a force that is along here. Okay, so it's aligned along this member, so it can't produce a moment there. QS2 produces a force up this way, so it can produce a moment, but we need to think about what this force actually means and how we actually then apply that. So S2 is going to produce a force acting along this member, and when we integrate it, let's call it FQ2 is equal to the integral QS2 from, let's say this whole thing is L long, from L to 0. Now it's a force acting in this direction. Okay, so that will have 2 components to it. So let's say that's FQ2. I have a vertical component and a horizontal component, with the angle being alpha here. And we can work these out from basic sort of trigonometry. This would be FQ2 sine alpha. This would be FQ2 cosine alpha. So similarly to how S1 couldn't produce a moment here, then the component that is going vertically, reacting through this node here, can't produce a force. So we need to take the component that's normal to, i.e. this part here, and this moment arm here. So the moment produced by this shear flow is equal to this bit multiplied by this moment arm. Okay? So let's say M1, and let's say the moments, we'll say they're acting counterclockwise, would be equal, for this just completely made up shape that I've just produced, would be equal to the integral of QS2 from L to 0. That gives me the force acting up this way. I then need to multiply it. Let's say here this is ds2. I then need to multiply that force by cosine alpha. And I then need to multiply it by that moment arm. Okay? So this is force along member 2 to 3. This bit here gives me the component of force that's acting normal to the moment arm. And then this bit here is just the moment arm of the force application. Okay, so this theory that we've just done here, we can sort of see how we take that shear flow, turn it to a force, turn it to a component of force, and then multiply it by a moment arm. We need to apply this to the shape that we've just done. So let me... Annoyingly, there's no way of selecting a group of text and moving it with this app. I've got to select it, copy it, and then move it. I might write to the people that make it and suggest they do that. Oh, I've crashed the whole thing. Excellent. You can see a nice old family photo in the background. Let's load this up again. Well, everything, I've just lost a bunch of stuff, so that's fine. Let's move along here. Okay, but we've got it in the video, so that's fine. So we've got our... so we've got our shear flow. That's the important thing, okay? What we now need to do is to determine how we react that as a moment. So we're going to look at moments at the very center of this comedy bottom. Backwards 3, whatever you want to call it. We have S1 and S2, and we've already said we only need to work out this one and we'll just double it. We're going to work out moments evaluated here. So I've got Vy multiplied by E has to be equal to whatever this is along here. So let's draw this. This is my radius R. This is, sorry, that's not what I'm doing. That's the wrong shape. This is where I happen to be. That is R. This here is my theta. So because this is a curved shape, the force that's being applied because of that shear flow is going to be equal to the tangent to this wherever we happen to be. So where I am here, let's pretend I drew a perfect tangent. That would then be the component, the actual force in this direction. So that is then going to be dFq2 on ds2, okay, because it's going to change. It's a function of that distributive force acting along here. Okay, so that's acting in that direction. The bit that we care about, the bit that's going to produce a moment, is we're looking for, this is my moment arm here. Let's call it L. We care about whatever component of this force is acting normal to it. Okay, so this is a right angle here. You can show, if you want to play around with circles, remember your chords, tangents of circles, this angle in here is equal to half whatever this angle is here. I'm going to tell you that for free, okay? Took me a little bit of time playing around with chords, tangents, circles to prove it, but you can show it, okay? And if you want to, if you're tenacious enough, go ahead and show it. That would be great. So we know that the component of force, which I've lost this, annoyingly I've lost this diagram, but the equivalent of cosine alpha for us is now going to be cosine alpha on 2. Sorry, cosine theta on 2. So we've worked this out. This is effectively our alpha now. And then the moment arm here is going to be L, and we don't know what L is yet. We can work it out though. So if this is L, let's say I've got this triangle again. So this height here is going to be R plus R cosine theta. Okay, R plus R cosine theta. I'll leave you guys to work that out. This bit down here, it's a messy diagram, but you guys get to see it being drawn as we go along. It's going to be R sine theta. So it follows that L squared is equal to R plus R cosine theta squared plus R sine theta squared. Let's multiply this out. R squared plus R squared cosine squared theta plus 2 R squared cosine theta. So that's me just multiplying out this quadratic. Let's put this second one. The second one's nice and easy actually. We've got R squared sine squared theta. So I've just multiplied that whole thing out. You should be able to see that I've got an R cosine squared theta and an R sine squared theta. Sine squared plus cosine squared theta is 1. So I end up with R squared theta plus R squared theta. Sorry, I've got R squared plus these two things just add up to give me R squared. So I end up with 2 R squared. And in fact, I've got 2R squared cosine theta. So let's simplify that in one step. Okay, so my L squared is equal to this. We want to square root it because we actually want the moment arm. L is therefore equal to the square root of 2R squared, 1 plus cosine theta, equals root 2 multiplied by R multiplied by the square root of 1 plus cosine squared. Sorry, not cosine squared, cosine theta. So we've got this far. This next bit's a little bit complicated. This involves some trigonometric identities. You've got to sort of remember your trigonometric half angle formulae. Well, you don't necessarily have to remember them, you just have to be able to look them up and remember how we get there. But again, I wouldn't expect you guys to do this part. I just expect you guys to be able to use perhaps the end result of this part. Okay, so we've got this far. Now I know that the trigonometric half angle formula, let me just look it up again. Again, I don't remember this stuff because I don't need to, and neither do you guys really, neither now. So we just need to know that there is a half angle formula that's going to be useful. So that is cos x on 2 is equal to the square root 1 plus cos x on 2. Okay, which is, this is almost what we've got here, but we need to divide the whole thing by 2. So I can just make this into root 2 multiplied by, it's going to be 2 over root 2, which is actually just the same as root 2. Okay, so this now is my length. Okay, it's 2 multiplied by r multiplied by cosine theta on 2. Okay, there's probably other ways you could show this length here, maybe involving this angle. Okay, because what we've got here is theta on 2. Now I trust you guys to go through and look this up and to copy this out and to work out how we go through this. Let's erase this bit. So what we've got now, we've got the moment arm, which is this bit here. Okay, we've got the part of the force that we need, so it's going to be cosine theta on 2, and we've got the shear flow distribution, which is up here. So we've got everything we need to do to determine this, but they're all functions of theta at this point, which we haven't got yet. So unlike previously, the angle is a function of theta, and also the moment arm is as well. So these all need to go into this function, so into the integration. So since the components of force normal to L, and L itself are a function of theta, we need to integrate the whole thing from 0 to pi. So we need to include them in the integral. So I'm going to say that my rate of change of the contribution to moments as a function of theta. Let's look at that, okay? So I'm going to draw this shape out again. So that's QS1. That's theta. This up here is L, which we have the function of theta of, and then this angle in here is theta on 2 in this case. So we now want to look at the contribution of the moment here, and we're going to treat moment as being positive. So we'll say d mq because of S1, dqs1 as a function of theta. So we're now looking at the contribution as the moment changes, is going to be equal to QS1, which is just the, again, remember that shear flow is just newtons per meter, so it's force per, or newtons per elemental length. We got QS1 as a function of theta, which we already have. So that's what we produced it as. We then need to convert it to this component here, so it's cosine theta on 2. And we then need to multiply it by the moment arm, which is 2r cosine theta on 2. So this is the expression that we've now got for our, which is what gives us a force, sorry, not force, gives us the moment contribution due to QS1 when resolved here. Okay, so this is now just a differential expression, dmq by d theta. To get the entire moment, we now need to, I'm going to simplify this first, and then we're going to integrate it. So let's say this is QS1 multiplied by 2r multiplied by cosine squared theta on 2. Now we've used this previously. We haven't used this briefly, but we can use one of the. Oh no, we have used this before. In fact, so cosine squared theta on 2. We've got the half angle formula up here. Square this side, square this one. This will give us 1 plus cosine theta on 2. Okay, so thankfully those 2's cancel. We get QS1 multiplied by r, 1 plus cosine theta. So this is the rate of change of the moment produced at this point as a function of going along here. So if we integrate this from 0 to pi, that will give us the moment due to QS1. And then we need to double the whole thing because we've got two of these. We've got two semicircles, they produce the exact same moment. And why we double them is because S1 is defined along this way, so S1 is going to produce a force that's producing a positive moment here, okay, as we've defined it. S2 is defined, I'm trying to look at this, S2 is defined along this way, so S2 will produce a moment in the other direction, but we've already said that, where did I write it? Because of symmetry, S2 is equal to minus S1, so the two moment contributions are going to be equal. So we'll just double the whole thing down here. Okay, so we're down here. So the sum of moments due to all the shear flows is equal to 2 multiplied by the integral from 0 to pi QS1. Let's take the r out here actually, because there's just a function of r, that's no longer a function of theta. 1 plus cosine theta d theta. Sorry, I should have that should be r d theta, okay? Because we actually need to integrate along s, okay? So this should be the moment due to q is equal to the integral from s max qs1 ds. ds is equal to r d theta. Okay, so we need to make sure we do that change of integration variable here, and I've got that here. Okay, so our QS1 is the only thing we haven't got written down here. Let's copy this down. QS1 is written here. I'm going to copy this whole thing. Okay, and let's go down here. Oh no, let's not do that. Here we go. That's my QS1. Let's tidy this up a little bit. Pencil's running out of the battery. Hopefully I can get this example finished. So that's my QS1. I can take this, substitute it in here, and then I can perform the integration. Equals 2 multiplied by r, integral from pi to 0, Vy on 3r pi, theta plus sine theta, 1 plus cosine theta, r d theta. Okay, those two r's cancel. I'm going to take the constants out and just turn this into and I'm going to expand this all in one step to try and get it done whilst this still has battery. 2 on 3 r Vy on pi, integral from pi to 0, theta plus sine theta plus theta cosine theta plus sine theta cosine theta d theta. Okay, so we're getting there. We are almost at the end of this dirty great expression. Let's just check I've got the same thing that I produced before. That's good, I do. So I'm not going to cause trouble now. So got this here. We now need to integrate this entire expression. Now this is not a nice thing to integrate. Like I say, guys, once you actually move beyond sort of your first couple of years of mathematics at university, you don't always need to remember all of those trig identities for how you evaluate things. I would be happy for you to say here, I can't quite remember how to necessarily do all of these. Put some of it into Wolfram Alpha if you needed to, but we can do the integral here, and we can then just say that we've got 2r Vy divided by 3 pi. This first one's simple, that's theta squared on 2. That's going to be plus cosine theta. Sorry, no, it's not. It's going to be minus cosine theta. Minus cosine theta. This theta cosine theta becomes theta sine theta plus cosine theta. And then this one becomes minus half cosine squared theta. And actually, because the limits for this are pi and 0, all of these trig terms cancel out, which is very handy. So that's good for us. okay, because the only one that's left is this, and we get plus a half, minus a half, and they cancel. These all cancel out as well. So we end up with the moment due to the entire shear flow is equal to 2 RVy on 3 pi multiplied by pi squared on 2, which gives us pi RVy on 3, which is suspiciously close to what we need to actually evaluate. So this is then the moment due to the combined shear flows. We've then got our terrible drawing of this shape here. We are evaluating moments here. I've said that Vy was in this direction. The moments that I'm evaluating are like this. Okay, so I've evaluated a positive moment here. Vy would produce a negative moment in this sense. So for those to be correct, or for those to be equal, I would have to have Vy multiplied by E is equal to minus pi r Vy on 3. E is equal to minus r Vy on 3, simply meaning that this distance is inside this object. It's just different in the way not r Vy on 3, r pi on 3, okay? The way that I've defined E is that it's slightly to the right here. Back in the question, here we go. Determine the position of the shear center S, okay? And it hasn't actually said which way to determine it, but for this object, it's got to be in this direction, okay? So it's inside the actual center of this object here. So we've determined a lot here. We've done a lot of tricky things, gone through a lot. I've sort of whisked through some of it, but I want you guys to be able to pick the parts you can use to help you understand it. Check you understand the solution, check which bits you don't understand, and ask me questions, because you're going to need to be able to use and evaluate shear flows in curved sections in order to do your homework. Okay, have fun guys. I'll see you all in a review in an hour anyway, and I'll probably direct you to watch this video.